Hello, I'm Dr. Scott Steedman, and this is a series about my heroes, fellow engineers and the greatest structures they built on Earth. The tallest, the biggest, and the most expensive buildings ever built. The kind of structures that beg the question, how did they build that?
In our first programme, we travel to Paris to take a look at the Eiffel Tower and then visit the Grand Serre, one of the finest examples of late 20th century structural engineering. But our story begins at the spectacular Garabit Viaduct in the heart of France. The development and mass production of iron and steel in the 19th century radically transformed the nature of engineering. These newly plentiful materials offered pioneers undreamt of opportunities to bridge any expanse and scale unbelievable heights. Alexander Gustav Boneckhausen-Eiffel was one such pioneer. Born in Dijon in 1832, he trained as a chemist, but a curious twist of fate drew him to the burgeoning railway industry. It was in building bridges and viaducts that he made his name, and that reputation won him a commission to bridge the gorge at Garabit.
The Garabit Viaduct, here in the Massif Central in the heart of France, was the finest of Eiffel's bridge designs. A spectacular bridge built with mathematical precision, this viaduct illustrates the best of the new, bold civil engineering which emerged in the 19th century.
The viaduct at Garabit was to be the highest iron arch bridge in the world. This design was an ideal way to span the steep gorge. A 563-metre-long railway deck sits on an enormous arch which straddles the Truyère River below. Eiffel used wrought iron because no other material had the strength and reliability to make the viaduct possible and allow the relentless progress of the railways to continue. The giant arch is pinned onto huge concrete abutments that are built onto the sides of the valley. The weight of the bridge passes down the arch into the abutments. The deck stands 122 metres high above the bottom of the gorge.
Engineers at that time did not have access to the complex computational methods of today, and they had to design a structure which they knew they could analyse. They had a shrewd idea of the direction of forces and the strength or resistance of materials, and their structures reflect that fact closely.
Eiffel opted for iron trusses for the huge arch, supporting piers and railway deck. A simple element, the iron truss is easy to analyse and can be used in almost any situation.
The whole truss has to be stiff enough and strong enough to carry its own weight and the weight of a train. The whole truss works like a beam trying to bend. So the top is in compression, it's being squashed, and the bottom is in tension, it's being stretched. The crisscross members in between work in either tension or compression, and one of their key functions is to keep the top and bottom in position. The stiffness of the whole bridge comes largely from the distance apart of the top and bottom, the depth of the truss. The bridge is made up of giant trusses, but within the giant trusses, there are also smaller trusses. It works on just the same principle. The top and bottom pieces, which carry the bending forces, are held apart by this cross-bracing in between.
All the pieces for Garabit were prefabricated, brought to the site and then riveted together.
It's like a giant Meccano set. Riveting was a skilled job. Must have been quite hairy doing it out here, this height. Riveting is a good process though, and the rust that can develop around rivets can help actually fuse it all together. It's a nice system for bonding metal. Let's go on. Eiffel was very concerned about wind forces, and he carried out experiments to determine the wind resistance of different sorts of truss. Here on the Great Arch and up there on the piers, you can see that they flare out, which gives the bridge the lateral stiffness that it needs to resist the fierce winds that funnel down the gorge. Eiffel's method of construction of the arch was ingenious, requiring no scaffolding underneath. Instead, he built each side up from the concrete abutments as two cantilevers suspended on steel cables from the piers on either side. The whole operation was extremely precise, and when they finally met in the middle, only a very small adjustment was needed. Finally, they put the deck over the top. You can feel the whole bridge vibrating under the weight of the train. Quite a funny feeling, really. Yeah, it's passed over now. Wow, that was quite exciting. Staircase is wobbling, but that you could feel these main girders vibrating quite strongly. Eiffel calculated that under the weight of a train, the center of the arch here would deflect just 8 millimeters, about that much, and he was proved exactly right. In a traditional arch bridge, the weight on top is carried down to the arch through the spandrels, the solid part between the deck and the arch, which you can see in the masonry bridges on either side. Here, solid spandrels would have been so huge that Eiffel's engineers concluded the forces would be incalculable. So they opted for no spandrels at all, and instead used this great depth of truss bent into the shape of an arch to give the bridge the stiffness it needed to carry the trains. The most dangerous moment in any construction project, in terms of the project as a whole, is often just before the construction is complete. Eiffel must have been very relieved when the two halves of the great arches were finally riveted together, and he'd accomplished his dream, the biggest iron arch bridge in the world. With the completion of the bridge at Garabit, Eiffel's reputation as one of the greatest civil engineers of his time was complete. It's a working bridge, of course, functional, like all of Eiffel's structures had been up to that time. Such a simple form of construction. Eiffel must have wondered how far he could go with it.
Paris at the end of the 19th century was the second largest city in the world, a city of wealth, a city of empire. There was a mood to celebrate the centenary of the Revolution of 1789 and France's new global status. A universal exposition of industry and commerce, a grand exhibition, was launched, and it needed a centerpiece. The invention of the lift and new skyscrapers in America must have inspired Eiffel. He jumped at the chance to build a huge and lasting monument, the Eiffel Tower.
Of course, the images that we have of the Eiffel Tower are usually from a distance, and it's not until you get underneath it, like this, that you really realize how huge it is. And the feeling of space under these great symmetrical legs is very impressive indeed.
Eiffel used 250 men to build the tower, and his engineers produced over 5,300 drawings of all the component parts. As at Garabit, everything was prefabricated and all the holes were pre-drilled. Parts were then brought to the site where they were lifted into position by cranes and riveted together.
Must be very exciting going up in the lift. They were just recently invented. Quite exciting today, really.
To a Parisian in 1889, the highest thing you'd ever have been in would be a 7-story apartment block, like the ones down here. This is a waxwork of Eiffel in his office at the top of the tower. He was very interested in scientific experiments, and one of his justifications for the tower was the study of the lower atmosphere. Although Eiffel is obviously closely associated with the tower, in fact it was originally conceived by two of his engineers, Monsieur Koechlin and Monsieur Nouguier, who'd sketched out a scheme for a super tower as early as 1884. Of course, they were all railway engineers, really, so they used the techniques they knew best. And what this reminds me most of is a gigantic railway pier, and we're right inside it. Eiffel's tower was to be the tallest structure in the world. Only iron or steel would be strong enough and rigid enough to support itself to these heights. Steel was a relatively new material, so Eiffel opted for what he knew best, puddled wrought iron.
Eiffel had an excellent and reliable source of top-quality iron in the foundries of Lorraine. Good quality iron was important because his whole reputation depended on the success of the project. Eiffel had made a deal with the city. He would put up 5 of the 6.5 million francs it would take to construct the tower. In return, he would keep revenues from visitors during the exposition and for 20 years thereafter. It was a massive financial gamble and the biggest risk of his career. So in order to ensure a profit from the venture, Eiffel had to keep his overheads down.
And one way Eiffel could keep costs to a minimum is to standardize as many of the components as possible. Looking up to the 3rd level, you can see many of the lattice girders are identical. Under each of the main floor levels are huge girders which span across the tower, tying the legs together. That's what makes the distinctive gaps in the lower levels of the Eiffel Tower possible. Looking up here from the 1st level towards the 2nd level, you can see the 4 legs very clearly. The weight of iron in the structure is 7,300 tons, and with the lifts and the other equipment, the weight of the tower in total is over 10,000 tons. Finally, back at ground level, behind me is the base of one of the legs, disguised with stone. If we go over to the north pier, we can get a closer look at the foundations. Inside the stone base of the legs, each of the 16 ribs sits in an iron shoe resting on a concrete foundation. The shoe carries a weight of over 600 tons here, and the thickness of the iron is 100 to 150 millimeters, about the same as this thickness here. During construction, each of the ribs was secured to the foundation using these bolts to stop them bending over as they were built up. Hydraulic jacks inside the shoe were able to align the structure perfectly. I don't usually go for this kind of thing, but there's something else I want to show you. The towers come to symbolize Paris, but it's the curved shape of the legs which is so well known. The obvious shape for a giant railway pier would be straight, like this. or inclined. But to resist the wind loading, these shapes would have to be braced to ground level. The wind acts on the side of the tower, trying to bend it over, just as if the tower was fixed to a wall and its weight was trying to bend it down. The curved shape of the legs acts like half an arch, carrying the force directly down to the foundation, so there's no need for bracing.
Eiffel's entrepreneurial skills made him a very rich man, but more importantly, he made a major contribution to the image of modern France, for which he is duly recognized. His tower was the last great wrought iron structure, which at the time represented the cutting edge of engineering, an ultra-modern building in a classical city. Since then, Paris has built on its reputation as home to some of the most spectacular modern structures, although iron is no longer the material of choice. On the other side of Paris, in the northeast corner of the city, is a structure that represents the very best in modern engineering. Almost 100 years after the Eiffel Tower was built, President Giscard d'Estaing decided to establish a new museum, the City of Science and Industry, to enable the French people to discover the industrial adventure of today and to celebrate the very best in modern science and technology. The museum was completed in March 1986.
This is a wonderful museum, a mixture of exhibits and exhibitionism. These great trusses on either side could have been plucked straight from the Eiffel Tower, but they look huge even for this building. But that's not why we're here. We're here to see the work of one of the greatest structural engineers of the 20th century, Peter Rice. The late Irish engineer, Peter Rice, was one of the most brilliant of his generation. He was instrumental in the realization of projects as varied as the Louvre Pyramid and the Sydney Opera House. Rice was invited by the architect, Adrien Fansilbert, to design Les Grandes Serres, 3 massive glass houses intended to unite the museum with the park outside. The spacious units represent the pinnacle of refinement in steelwork. They are light to the point of seeming to lack substance, making even the airy structures of the Eiffel Tower and Garabit Viaduct appear bulky. The contrast between the heavy industrial trusses inside and these beautiful, refined glass serres is total. From the engineering perspective, this is what makes the building so remarkable.
The structure of the glass houses is light years ahead of the Eiffel Tower, but still beautifully simple.
Glass is in fact a very strong material in its pure form, but in practice it's rather weak and extremely brittle and breaks in an explosive way when any scratch or defect, however microscopic, causes a stress concentration. Steel can take huge loads in tension and compression, and it has the property of ductility. It will stretch before it breaks. This gives protection against overloading, a sort of warning, if you like, that the material is about to break. The challenge is to bring these two very different materials together.
Each of the 3 serres has 24 steel frames which hold 16 glass panels, each one 2 meters wide by 2 meters high. The 16 panels in each frame weigh 2 tons.
Carrying that vertical weight and coping with the wind load from outside is what this lightweight steel frame and connections are all about.
In simple terms, the glass plates have to carry their own weight and the force from the wind outside. The glass plates hang one on another
and their weight is carried right up to the top. There's a spring up there which locates the top panel. The wind force is taken completely separately through this stainless steel cable truss. The two systems are totally independent, and they only come together in the tubular steel frame around the outside. The connection is really very clever. Inside each of these 5 points is a ball and socket joint, inside the glass here and inside this metal unit. Like a hip joint, a ball and socket joint enables the glass sheets to move independently, so the whole system is articulated. This is the tubular steel frame that surrounds the glass walls. You can see where the glass meets the building itself. There's a flexible seal, and the joint here is free to rotate, so the whole wall can move inwards with the wind.
Rice had a great admiration for the 19th century engineers like Eiffel. He talked of their structures as having a simple honesty that goes straight to the heart of the physical characteristics of the material. But his own work is more Swiss watch than railway pier.
The meticulous attention to detail and sophisticated calculation in this design allowed Rice to refine every element. Like a racing yacht, each component has a precisely defined function. There's no excess baggage. There's some irony then that in a museum celebrating science and engineering, Rice's brilliant and innovative design isn't acknowledged or explained anywhere.
Rice also believed that the role of the engineer extended to building structures that people warmed to and that conveyed a feeling of having been designed by one who cared.
Rice's genius for structural engineering is clear. He had a mission to enrich people's experience of the structures around them, which is where he differed from Eiffel.
However, both Rice and Eiffel were like artists, masters of their materials and the knowledge available to them. But new materials and techniques are evolving all the time. Who knows what brilliant structures people will be enjoying 100 years from now? Next week, we look at the nature of defence. We start at a dramatic medieval Scottish castle, travel to France to see a spectacular fortress, and finish at the massive barrier that protects the people of Holland from the sea.
People have always felt the need to feel protected from marauding armies or the ravages of nature. When it comes to defending communities, engineering has a key role to play.
In this program, we travel to the huge Citadelle de Blaye in France to look at the work of the great military engineer Marshal Vauban. Then we move to Holland to grapple with the task of defending a nation against the sea. But we start our story in medieval Scotland. Here on the east coast of Scotland, Tantallon Castle stands on a rocky promontory, protected on 3 sides by the sea. This magnificent castle dates from the mid-14th century, built to protect the family of successive generations of a local warlord, the Douglas Earls of Angus.
The 14th century in Britain was a dark and difficult time, and those with the means protected themselves and their families by building huge castles to defend their territory against aggressors. Most people's idea of a castle is 4 walls surrounded by a moat. While many castles use nature to their advantage, at Tantallon this is taken to the extreme. With cliffs on 3 sides, they only needed one huge wall across the promontory to provide a barrier against attack. In the 14th century, the principles of defense had been unchanged for hundreds of years. Castle walls needed to be high enough and sheer enough to repel boarders, and solid enough to resist the force of boulders hurled by catapult.
Just climbing up inside the Great Wall. Wonderful tower up here, absolutely amazing. His keep at the east end of the curtain wall is exactly the same width as the wall. Must be all of 12 feet wide.
At 12 meters high, the red sandstone wall was an imposing feature on the landscape. With this great curtain wall to protect them and the sea around them, the Earls of Angus and their people lived in this community for over 170 years in comfort and security. Tantallon's reputation grew as one of Scotland's greatest baronial mansions. But following its construction in 1350, gunpowder swept across Europe, revolutionizing warfare, and in 1528, Tantallon faced its first serious test.
Seeking to assert his authority over the 6th Earl, the young King James V assaulted the castle with a small force, including 3 cannon, and besieged it for 20 days. It was the first time Tantallon had been attacked by cannon. The castle survived unscathed, but it was clear that strengthening works were needed to resist this new form of weaponry. They strengthened the castle by building a new tower in front of the old one, using the distinctive green mudstone that you can see beneath me.
The green mudstone was a clever choice. It's much softer than the red sandstone and would help to absorb the impact of cannon fire. You can see how the mudstone has weathered much more quickly than the red sandstone.
This is one of the rooms which has been infilled with masonry in an attempt to increase the mass of the curtain wall. What a mess. Perhaps they were concerned that with the new cannons they would just blast through the door, and they therefore assumed that their walls were going to be strong enough. They'd add some stonework and fill in those empty rooms and so on. But they'd put most of their money into this piece of work here to protect the gateway. This is part of the defences of the castle after 1528. That could do you a lot of damage. It must have been unbelievable in here when that exploded.
In the years after the strengthening in 1528, Tantallon was regarded as so well fortified that Henry VIII chose it as the place to store his gold, destined to buy the loyalty of unreliable Scottish lords. But in 1651, Tantallon finally fell to one of Cromwell's armies. Continuous bombardment by 16 cannon over 12 days finally breached the Great Wall.
The reason was that the repeated impact, high-energy impact of the cannonballs on the same spot of the exposed vertical wall was inevitably going to break through eventually. Medieval design was no match for the new technology.
By the time Cromwell's army had laid waste to the once mighty defences at Tantallon, the castle was some 300 years old and hopelessly out of date. On mainland Europe, great fortresses had been built that tackled the problem of cannon fire with defences on a different scale altogether. By the 17th century, warfare on the continent of Europe was a fact of life. It was the age of the siege. The medieval castle was overtaken by an altogether more advanced concept of defense which required a new type of person, the military engineer.
It was also a mathematical age, the dawn of the age of reason, the time of Galileo, Descartes, Newton. Mathematical calculation was the key to unlocking the logical harmony of the universe. Symmetry and proportion were the key to design, and fortifications were no exception. Here at the Citadelle de Blaye in southwest France, there's a classic example of the work of one of the greatest military engineers of all time, Marshal Vauban. The primary function of the fortress at Blaye was to guard the mouth of the Gironde estuary and the city of Bordeaux upriver. Vauban's mathematical approach places him in a unique position historically, as one of the first to apply a systematic design method to his work.
Vauban was a veteran of many sieges and was appointed by Louis XIV personally to oversee the construction of a network of fortresses around the country to defend the nation against invading armies, an awesome responsibility that made him one of the most important men in the country. Castle design had come a long way since Tantallon, and fortresses now altered the landscape with massive earthworks to protect against attack. Vauban's contribution was to take state-of-the-art defense ideas and improve them by applying geometrical rules, standardizing the form and method of fortress construction, enabling the entire national defenses to be built to precise instructions.
The system of defenses was highly geometric and meticulously thought out.
Blaye is protected on one side by the Gironde River. On the other side, huge curtain walls surround the fortress with triangular bastions at each corner. Bastions were huge buffers situated in front of the curtain wall. There are 4 at Blaye. Between and in front of the bastions were ravelins. These arrowhead-shaped defences were like small bastions and lower than the defences behind, enabling them to be shot over. Around the whole fortress was a great ditch. Around the outside of the ditch was the glacis, a huge mound built up and around the outside of the fortress to prevent a direct line of fire at the base of the walls. Blaye is so big that it's hard to visualize it from the ground. By drawing an overhead plan, we can also see Vauban's method for setting out the fortress. First, he laid out the corners of the bastions at regular distances. Then he mapped out construction lines between the corners, and from those lines used his standardized units of measure to determine the angles along which to construct the bastions and the curtain wall. Next, he worked out the position of the ravelins. This was determined by the line of fire from the sides of the bastions. Around the whole fortress, he built up the glacis. And added bridges to connect the ravelins to the curtain wall over the ditch.
The key difference between the medieval castle and this fortress is that behind the walls it's backfilled with earth, as you can see on the ravelin behind me. Even if you were to breach the wall with cannon fire, you couldn't just run through. It's a mountain. But these earthworks introduced a new problem, which is where Vauban made his second great contribution to engineering.
A wall retaining earth has to support not only itself, but also the pressure of the soil behind it. Too thin and it will be pushed over. Too thick and the amount of masonry will be unnecessarily expensive and time-consuming to construct.
Engineering is all about risk and return, and the price of failure in this case would be defeat in battle. Vauban was committed to building over 100 fortresses around France, so a standardized approach to design was essential. Vauban decided on a geometric solution to the angle of the wall, depending on its height and the width at the top. This is the top of the wall, the front, and the base. The back of the wall is buried, but it's vertical, like this. Behind the wall is earth, right to the top.
The slope of the wall was to be 1 to 5.
Giving it the stability against overturning that Vauban required. It's hard to find anywhere where we can see the width of the wall clearly, but on top of this ravelin, we can see that the wall is 1 metre wide. It's 7 metres high. Let's go and look at the bottom. The wall's been cut through here to make a door, but we can see the back of the wall is about here, and the front is over here, and it's more than 2.5 metres thick at the bottom. From the ditch, we get a good idea of the huge scale of the construction. Vauban's works started here in 1685 and took 500 masons 4 years to complete. Fortunately, they had a good supply of stone in the local quarries. Blaye was one of Vauban's early works and is remarkably well preserved. Outside lay the region of Bordeaux and the local community. Inside was the garrison, up to 1,400 men.
Blaye was never taken. Vauban's network of fortresses gave France the security it needed.
Vauban's contribution was that he was the first to appreciate the problem of the pressure of earth on a wall and to propose design solutions. Today he would have been known as a civil engineer. His great insights into siege warfare come from his unparalleled experience both as an attacker and as a defender, fighting in 50 important sieges in 52 years. During his career, he built or adapted over 150 fortresses in and around France, requiring 10 million tons of masonry, a huge amount of construction work.
Vauban's system of defences and the castle in general became redundant when the invention of the howitzer enabled shells to be lobbed over the walls from a distance. Today, massive earth defences are more likely to be defending nations from nature than from marauding armies, but the engineering problems are every bit as challenging.
The Dutch people have always lived with the threat of being overrun by water. But on the 1st of February 1953, a huge storm surge took them by surprise, breaching the sea defences in 67 places. 1,800 people drowned. For centuries, the Dutch had relied on dunes and local dikes for protection from the sea, but it was clear this was not enough. The survival of a nation was at stake.
The Dutch government concluded that the entire coastline should be protected by a system of dikes and barriers to be called the Delta Sea Project. It was to be hugely expensive, but the alternative was too terrible to contemplate. The Dutch have a long history of dike design. Dikes have to support not only their own weight, but the force of water against them. Any weak spot in the dike and the whole system of defences can crumble.
The big question is how high the dike should be. In 1953, recognizing the problem of rising sea levels and the unpredictability of great storms, the Dutch government opted for a level at least 1 metre higher than the terrible flood. There was a huge amount at stake. The length of the coastline is enormous. A balance has to be struck between the cost and time of construction of a high dike and the value you place on people's safety. It's a tough decision, whether it's your own home or your country that's at stake.
One of the last closures was the most difficult of all, the estuary of the East Scheldt, or Oosterschelde. The original plan was for a dam to keep out the tide, but this would destroy the sensitive ecosystem of the estuary. Instead, the Dutch opted for a vast barrier with gates that could close in the event of a storm surge.
The strong currents and the shifting sand in the East Scheldt made the construction of the barrier extremely difficult. As you'll remember from walking on the beach, when you fiddle around with your feet in the sand, you sink in, and the sea can easily wash it around your feet. So you need to densify it, you need to compact it first of all, to provide the base that you need for a great structure like this. And that's exactly what they did.
The contractors compacted the seabed and laid a vast mattress of stones and sand to provide a solid foundation on which to place the 65 piers that link the barrier gates over a distance of 3 kilometers.
For almost all their lives, these gates will be open, and the sea is free to pass in and out of the estuary beneath us. But when the storm surge comes, the gates are all that is between the people of Holland to my right and the sea out there. They have to work. Like a guillotine, each of the 500-ton gates is lowered into position. They'd have a lot of warning, maybe hours, of the arrival of the storm surge, but they can shut the whole barrier in 90 minutes. Of course, it doesn't have to be watertight. They only have to hold out the surge during the high tide. After the tide has passed, then the danger has receded.
Thankfully, the gates have never had to be used in anger, although they have a drill every year to make sure the gates will function in the event of a surge.
Behind the huge black gates here, with the estuary to my left and the sea out there, we can see the top of the great concrete piers. Each of them is the height of a 15-story building, but there's only a quarter visible above the sea. The water here is up to 30 meters deep. The piers support the machinery for the gates up there and a concrete road bridge over here.
The gigantic piers are hollow and were constructed in huge dry docks before being floated out into position. The construction and installation of the piers took over 4 years.
There's 18,000 tons of concrete in each one. At the base, they're shaped like a gold ingot lined up in this direction to give them the stability against the storm forces from the sea. Once they were in position, they were sunk onto the seabed and ballasted with another 12,000 tons of sand in each one. To protect them against scour from the tides, they imported at huge cost stone from as far away as Finland. It took 5 million tons to cover the entire 3-kilometer length of the barrier. But the biggest challenge was to align them perfectly within centimeters to allow the great steel gates to go up and down. Out here, practically in the open sea. Oh, it's windy. This is the base of the hydraulic cylinder and the piston that holds the gate up in position in its normal state. It's connected to the gate by the giant pin down there. So when the gate's triggered, the whole thing drops into the sea. Whoosh! Brilliant. The framing on the front of the gate gives it the stiffness that it needs against the force of the storm surge. It's very dramatic. You can see the tide now driving in underneath it. The tide's now going at full tilt, and you can really get an idea of the forces on the concrete sill beneath me and on the piers and on the stone out there in the sea. Just imagine that huge weight of water flooding through. In fact, it's very like what would happen if a dike was breached. You could imagine that flooding a polder in no time at all. And if you think this is exciting, on the last pier there's a marker where the 1953 flood level in this part of Holland reached. We're a long way below it today, luckily.
The barrier was completed in 1986 at a third of the cost of the entire Delta Sea project and 3 times as much as the cost of a simple dam. But it's a testament to modern civil engineering, providing defense for the people of Holland while maintaining the natural habitat of the tidal estuary.
Not many countries can afford the Dutch approach, but balancing the environmental issues with society's aspirations for security, whether physical or financial, is at the heart of the civil engineer's role throughout the world.
One thing is for certain. The battle to ensure the survival of the human race as our environment continues to change means the civil engineer will remain on the front line, defending us from the elements. Next, we look at the Cantilever Bridge in its many guises. We start with the simple but elegant Kingsgate Footbridge in Durham, northeast England, then explore the vast expanse of the Forth Rail Bridge in Scotland, and finish in Seville, Spain, to look at the outlandish Alamillo Bridge.
A cantilever is the simplest of all supports. Like a bracket supporting a bookshelf, a cantilever is fixed at one end and projects outwards into space. It's an obvious technique for building bridges.
In this programme, we travel to Scotland to see the bold Victorian engineering of the Forth Rail Bridge, then fly to Seville, Spain, to see the outlandish Alamillo Bridge. But we start our story at the elegant Kingsgate Footbridge in Durham, northeast England. Here in Durham, where the River Wear loops around the great cathedral, there's an outstanding example of the simplicity of the cantilever bridge in the Kingsgate Footbridge.
In 1963, the university wanted to build a link to the extension of the campus on the other side of the river. They had little money, but they thought it might stretch to a span from bank to bank. Of course, being in a gorge, that would have meant the students having to walk all the way down one side and all the way up the other. And you know what students are like.
The university commissioned Ove Arup, one of the greatest civil engineers of the 20th century. Born in Newcastle of Scandinavian parents, Arup came to engineering from philosophy. The Kingsgate Footbridge was the last great structure that he designed himself, and its success in such a dramatic and sensitive setting is a testament to a remarkable career.
Arup's solution was a simple double cantilever bridge spanning right across the top of the gorge. The deck acts as a beam, and the whole weight of the bridge is carried down the supports. Inclining the supports is not merely for aesthetic reasons. It means there are only two foundations, and it divides the span into 4 sections.
In the words of the designers, the bridge is like a thin, taut white band stretched across the valley, resting on a pair of slender, tapered fingers in a V shape, rising from each bank of the river. The best way to see how the cantilever principle applies to the bridge is to look up at the supports from below.
This is half of the bridge, like this. And the weight of the deck is supported on two twin supports, like this, which come down to the foundation. The weight of each end of the deck cantilevered off the end here from the supports is balanced by the weight at the other end. And the weight of the whole deck is carried down to the foundation. It's a double cantilever, and this is one half, and it's exactly balanced by the weight of the other half. This is the base of one of the two double cantilevers of the bridge with its foundation block below. Each of the two foundations supporting the bridge have these great V-shaped supports with two fingers on each which stretch away to the deck above. Beautifully designed. Arup paid a huge amount of attention to the detail in the design, every line carefully laid out. The bridge was actually constructed this way along the bank of the river, over the bank, so there was no need to obstruct the river at all, making it a lot cheaper. And then it was turned out to the river like this in a single movement. And it was brilliant, really, because inside here were two cones, one on top of the other, with the outer one turning like this, 90 degrees, just once, and the two spans meeting in the middle. And then this was grouted up through holes so that it all became a solid lump. And the bridge looks wonderful today. I'm standing here at one end of the double cantilever. Each of the two halves of the bridge is completely structurally independent of each other. It's much more flexible than it would have been if it was all rigidly connected together. A large group of school children have just walked across, and you can really feel the bridge move quite perceptibly. The deck of the bridge is like a U-shaped beam, with each of the side walls providing a lot of the strength. Inside the walls, which are called the flange of the beam, there's steel reinforcement, and in the floor, underneath the paving stones, there's more reinforcement to help the beam carry the weight of the people in bending.
The genius of Arup's bridge was to achieve this beautiful solution for the same budget that the university had set aside for a simple bridge across the bottom of the gorge. The Kingsgate footbridge clearly illustrates how dividing up a span into sections can be an ideal solution to bridging a gap. But this is an example of the cantilever on a small scale. The colossal Forth rail bridge spans the Firth of Forth near the Scottish capital city of Edinburgh. The bridge is made up of three huge double cantilevers connected by girder bridges, and at the time of its construction was the biggest bridge in the world.
The ambition to cross the Firth of Forth has existed for centuries. The direct route across the estuary is just a few miles, but conditions in winter in particular can be pretty rough and treacherous. The alternative is a long detour, maybe 50 miles, around the shore. As the railways expanded in the 19th century, it became increasingly important to construct a permanent crossing. Passengers and freight
had to transfer from the railways to a ferry to cross over, and it was very time-consuming and expensive.
As early as 1805, there were proposals for a double tunnel, quaintly described as one for the comers and one for the goers, but that plan wasn't feasible.
But it wasn't until the middle of the century that the railway companies finally decided to go ahead and let a contract to the country's foremost bridge engineer, Thomas Bouch.
Bouch began work on a huge double suspension bridge, but soon after the start, work came to an abrupt and tragic halt when another of his bridges, the Tay Bridge, collapsed. A busy passenger train plummeted into the Tay, and 76 people were killed. Faith in Bouch evaporated, and the project was abandoned. Bouch died a year later. The ambition to cross the Forth did not die with him, however, and in 1882, some 10 years later, a new bridge contract was awarded to John Fowler and Benjamin Baker. The two were leading civil engineers, and they began work on a different bridge design to Bouch's double suspension bridge. Instead, they opted for 3 vast double cantilevers, and with this new design, they set about trying to restore confidence in the railways. Each of the 3 huge double cantilevers of the Forth Rail Bridge weigh around 17,000 tons and are immensely stable because of their great self-weight.
Each of the huge cantilevers needs a system of bracing internally to make it stiff enough to carry the weight of the railway traffic. The bracing's very simple. The solid tubular members work in compression, and the open lattice girders work in tension. And together, they form a system which is stiff enough to take the weight of the trains. At each end of the bridge, masonry arches disguise 1,000 tons of pig iron weighting down the end of the cantilever against the weight of a train and the girder bridges trying to tip it up. This is where the girder bridge connecting the South Queensferry cantilever meets the main central cantilever at Inchgarvie. These standard girder bridges were used to keep the size of the main cantilevers as small as possible, and it's here that we can see how the bridge accommodates movement and expansion. The sheer size of the bridge, it's a mile long, means that the wind can blow on one end and not on the other. So it's essential that the cantilevers can act independently of each other, a bit like the carriages on a railway train. This is the end of the girder bridge, and there's a gap between it and the cantilever here. The girder bridge actually hangs off the cantilever on a ball and socket joint like this, so it can move backwards and forwards. But the girder bridge can also twist sideways relative to the cantilever like this, around this pin here, and another one at the top. To the top of the here, I'm hoping to get out and see the top of the bridge. We're just ascending one of the big tubular columns on the big cantilever on the Queensferry side. It's not particularly windy today,
It's only gusting to about 50 miles an hour. But all the bracing that you can see, the lattice bracing and the huge tubular bracing, is designed to make the bridge as rigid and stiff as possible. We're getting up near to the top now. Now you can see clearly the cross bracing in between the great columns behind me. Wow, gee. The top of the towers are nearly 400 feet above the sea. That's over 100 meters. And you can see them sloping together to provide stability. But the main stability against the wind is in the cross bracing that you can see beneath me here, in between the towers. We came up the easy way, of course. We came up the lift, but when they were building it, they would have had to come up the tubes themselves every day, thousands of men working their way up, riveting the bridge in sections, assembling it, building these lattice girders, standing and walking along these girders without the sort of protection that I've got here today. 57 men died building this over 10 years. It was a big human price, really. Right, Ralph? Thanks, lovely. Great. So we turn it around and then we'll head out that way. This is the central pier at Inchgarvie. 4 huge foundations for the 18,000 tons of steelwork above us. These granite blocks are there to protect against the waves, of course. Down below us is the enormous caisson foundation, concrete filled, which was floated out and sunk in position here. And then with compressed air to create a working space, men went down below the sea level, below the seabed, and they hand dug the foundations, sinking the caisson into the seabed. Amazingly, no men were lost at all in the sinking of the caissons and the construction of the foundations. Men were sick, of course, because it was horrendous working conditions down there, and working under the seabed in the winter, very difficult indeed. When they'd finished, then they would fill the caisson with concrete, facing it with these granite blocks to form this enormous foundation. This is all that remains of one of Boucher's piers for his suspension bridge crossing. Faced in brick, it's quite a different design to the granite facing of our bridge here. Rather sad, really. The last rivet was hammered in on the 4th of March 1891 by the Prince of Wales. The bridge had taken 10 years, £3 million, that's about £200 million today, and cost 57 lives. But they had achieved the crossing, and with the greatest railway bridge in the world. And it did restore faith in the railways and in British engineering, and it remains one of the world's most famous structures. Nearly 200 trains a day still use the bridge. Today, new steels allow designers to create bridges that are lighter in weight and easier to build. Nothing epitomizes that more than our next bridge.
One of the primary functions of the fourth rail bridge design was to restore confidence in bridge engineering. The bridge looks like it will stand forever. But in Seville, Spain, there is a bridge that challenges notions of what a bridge should look like. This is Spanish engineer Santiago Calatrava's dynamic Puente del Alamillo on the Guadalquivir River. It was completed in 1992 for Expo 92, a festival celebrating commerce and industry, and is a fantastic example of a cable-stayed bridge. It works on the same principle as the cantilever bridge, but in this bridge, the support for the deck comes from the tension of the cables above and the counterweight of the great pylon. Also, unlike the two bridges we've already seen, the Alamillo Bridge is asymmetrical. Santiago Calatrava was born near Valencia, where he studied architecture. He also read civil engineering, and it's his extraordinary ability to combine structural form with architectural qualities that has marked him out as one of the foremost engineers of the late 20th century.
The cable-stay bridge has actually been around for centuries, and many early bridges had cable-stayed elements. The concept is simple, but it's difficult to analyze, which kept the bridge in the wings until modern materials and analytical techniques realized its potential. It's now one of the most favored bridge forms of all.
It's not the 200-meter span of the Alamillo which strikes you. It's the great single pylon leaning at what seems like an outrageous angle. But it's this apparent instability which is the key to the bridge's success. The enormous pylon stands at an angle of 58¼ degrees and supports 13 pairs of parallel cables which run down to the deck like harp strings. The weight of the deck is exactly balanced by the weight of the pylon, so there is no need for a second set of cables at the back to anchor it.
Inside is just like a ship, miles of steel staircases. I'm told it gets smaller at the top. The tower was built by welding steel plate to form two tubes, one inside the other, and were right inside the center of the tower. And the gap between them, which is up to 2 meters, was filled with concrete, creating a composite structure, where the concrete gives the tower mass and stiffness, and the steel gives it strength. This is one of the welded joints between the steel plates. Phew, finally at the top. The bridge was meant to be a landmark, drawing you over the river to the expo site on this side.
The top of the bridge is 150 meters above the ground, and the cables stretch down to the deck below. The concrete is heavily reinforced at the base and where the cables are anchored to the tower. Under the bridge, the cables are fixed on either side of the spine of the deck into special anchorages.
A critical feature of the cable-stay bridge is its rigidity. It would buckle upwards under the huge forces from the cables pulling it back to the tower behind me, or twist sideways under the weight of traffic if it wasn't restrained properly. To achieve this, the spine of the bridge, where the walkway is a huge, hollow, hexagonal steel box girder, which has excellent torsional or twisting rigidity. The roadways on either side are cantilevered off steel ribs at 4-meter centers, like a fishbone. Here, under the spine of the bridge, we can see the depth of the central girder and the ribs on either side much more clearly. In design, it's not just the grand form that's important, but the details. And these holes in the deck and in the ribs above let the sun through to the water and lighten the whole appearance of the structure. Crossing bridges is an everyday experience, and yet often they're utilitarian, anonymous structures which we scarcely notice. The common denominator of successful engineering design is thought. Ingenuity and vision transformed all these structures from what they could have been to what they are.
In next week's program, we look at domes. We start our story at Brunelleschi's famous Duomo in Florence, then travel to Paris to explore the extraordinary Knit building and catch work in progress at the Millennium Dome in London.
Throughout history, there's been one form of structure synonymous with great public events. It's the dome. Domes have an almost mystical ability to create a sense of awe in the humble visitor. And to engineers, meeting the demand for ever larger domes has been an enduring challenge. I'm in London at the site of the Millennium Dome, and in this program, we'll explore the mystery and the glory of this and two other great domes. But we'll begin in Florence.
No other city in Europe, with the exception of Venice, trades off the past in the way that Florence does. In addition to its fantastic array of buildings, the list of geniuses who lived and worked here reads like a who's who of art and literature. Dante, Michelangelo, Botticelli, and Giotto, to name but a few. But to any visitor like me, picking their way through the Florentine streets, there is one incredible building tantalizing you on every turn. It's dominated the skyline of the city for over 500 years, the spectacular Duomo by Brunelleschi. In a design which brought together science and art to create a new standard for the future, the dome of the Cathedral of Santa Maria del Fiore marked the arrival of the Italian Renaissance. In completing the building, the city of Florence announced to the world that it could equal and even outdo the greatest achievements of the Roman Empire.
The cathedral itself, begun in 1296, took 50 years to complete, and that didn't include the highlight, the soaring octagonal dome.
At that time, domes were built by supporting the underside with timber scaffolding. But in Florence, the span was so great that no formwork could bridge it completely, so the cathedral had to go domeless even after completion in 1357.
Quite simply, they'd started a project with no idea of how to finish it, and it was to be another 60 years before a competition was launched in 1418 to find a viable design for the dome.
The winner was Filippo Brunelleschi. Armed with a 12-foot diameter model and a series of impressive innovations, he eventually won the contract that would take a further 16 years to complete.
Brunelleschi's major achievement was to complete the dome without any timber supporting structure. He argued
that a dome built up in stages, in rings, would be entirely self-supporting. This technique had never been used on this scale before. Although there was no timber structure supporting the roof, Brunelleschi built a working platform for the masons, cantilevered out on great wooden beams socketed into the side of the cathedral here. There are 48 of them right round the wall. The holes are huge. Imagine what the beams were like fitted in there.
One major innovation was a double skin. The dome has an inner and an outer shell. But at over 4 meters thick, it is also extraordinarily heavy, weighing 25,000 tons.
You see, domes carry their weight downwards and outwards, and they need to be buttressed or supported around their perimeter to stop them cracking vertically.
Historically, great domes had been buttressed around their sides, and here in Florence there are 3 small domed apses which provide some support.
Brunelleschi realized that this support was not enough. He used a system of stone chains with iron links like this around the perimeter of the dome, tying the whole structure together.
But all these systems were not sufficient to stop some movement from taking place, and you can see cracking up the middle of several faces.
People often think of cracking as evidence of imminent collapse. It may not look perfect, but masonry can really take quite large movements before it actually falls down.
It's incredible. Vasari's frescoes really use the octagonal shape. Hell portrayed at the bottom, moving up through heaven and topped by that fantastic false lantern. Access to the interior of the dome is by a sequence of staircases up through the stonework.
I've climbed right up inside Brunelleschi's dome, between the inner skin and the outer skin. Bricks have a very distinctive herringbone pattern, like the Romans used. Let's go on round the dome, through one of the great internal ribs between the inner and the outer shell that helps to stiffen it, and the dome stretching away above us. Fabulous. Look, and here's a window. You can see right down inside. The inner skin is really thick here, over 2 meters thick. You can see how clearly the masons have laid the bricks downwards in a line that lines up exactly with the bottom of the dome over there. It's just fantastic to be inside here and see this structure. I'm right inside the lantern at the very top of the dome. The lantern lets light down into the cathedral down there. Domes may look a bit like arches, but it's here we can see the fundamental difference. An arch always has a keystone right here in this space to stop the 2 sides falling in. A dome can have a hole because the forces are spread throughout the shell.
However, Brunelleschi's octagonal dome was an extra challenge. Smooth, rounded domes can carry their weight more efficiently and can be much thinner.
But in the end, it's the great thickness of this dome that makes it work.
Looking at the structure now, its 45-meter span could be considered modest in today's terms. However, for the best part of 400 years, the Cathedral of Santa Maria del Fiore had the largest dome in the world. An amazing and unique achievement, the dome still dominates the city skyline in a manner unequaled anywhere else and is recognized worldwide as the greatest masonry dome in existence.
The method of construction used here set a pattern which continued right up to the building of the great cathedrals of St. Peter's and St. Paul's. It's only recently, with the advent of new materials, that domes and their design have undergone some radical and spectacular changes.
This is La Défense in Paris, a city as famous for its more recent innovative architecture as for its traditional buildings. Steel and concrete, glass and fabric are the materials of this modern development. But there's one building in particular I've come here to see, a classic of design dating from the 1950s, which shows just how modern materials can reshape the traditional dome. This is the Centre des Nouvelles Industries et Technologies, known locally as the Knit Building. It was conceived as an exhibition space for French industry, built to show off France's engineering and scientific prowess in the booming 50s. More recently, it's become a retail development, housing shops and hotels.
What we're interested in is the futuristic design of the roof. While it's not a traditional dome like the Duomo in Florence, its rounded shape means it still works as a dome. It's also much thinner. In proportion to its span, it's as thin as an eggshell.
The steel and glass walls don't take any of the weight of the roof. They were part of the redevelopment of the building in 1988 and are there simply for aesthetic reasons. And of course to keep out the wind and rain. It's quite breathtaking to see it for the first time, like the vault of some giant Gothic cathedral. In essence, it's triangular in shape, with the weight of the roof channeled down to abutments buried in the ground at each corner. The sides soar up and over the top, giving it a clear span on each side of 218 meters and a height of 50 meters.
And there's only one way to get to the top. I'm right at the top of the roof, and what strikes you immediately is the huge, magnificent Grande Arche de la Défense right beside us. And here the great curved roof of the Knit building stretches away beneath us like a cloud, a great snowscape. This is the wall between the two panels, the crown wall, which carries the huge compressive force as they lean together. Let's go on.
In great buildings like this, there is always a strong relationship between the architecture and the engineering. The concept of this roof was easy to draw, but much more difficult to build. In the end, it was a French engineer, Nicolas Esquelin, who came up with the solution that we see today.
It was built in sections. First, the 6 curved panels, which meet here in the middle, and then the next 3 on either side, and finally the last 3 right out to the edge, way over there. Let's have a look inside. Inside the roof, you can see that it's made up of 2 shells, just like the Duomo in Florence, but they're much, much thinner. They're made of reinforced concrete, and down at the bottom, they're 600 millimeters thick. But up here, they're just 60 millimeters thick. That's this much.
The ribs between the top and bottom shells run all the way down to the corners. With the cross walls, they form a honeycomb, very stiff and yet lightweight.
Of course, it's not built up using bricks like the Duomo. Instead, they poured concrete onto curved wooden shutters supported on scaffolding underneath. It must have been a colossal undertaking. To keep their shape, all domes require secure foundations, and the Knit dome is no exception. The weight of the roof is channeled down the three sides to the ground. As the dome tries to sag, it pushes outwards at the corners, and the force outwards at each corner is equal to the weight of the Eiffel Tower. Inside, the shape of the vaults reminds me of three colossal fans meeting at the top. It's quite spectacular. The curved shape of the panels is also very distinctive, and it's there for a good reason. You see, the thin panels in the roof have to carry a lot of force along their length, all the way down to the ground. The problem is that a flat panel would buckle easily, like this. But if you make the panel curved, like that, then it's much stronger. And that's the principle they used here. Neat, isn't it? It's a bold design, even today. And like the Duomo, persuading people that it would stand up was a triumph, even in the 1950s. While the Knit building doesn't look like a dome, the main reason that it stands up is because it is a dome structurally. The forces are spread down through the roof. So domes don't have to be round, and they can be very thin. In fact, as domes get larger, they have to get thinner to be economical. But if you want to make them really large and really thin, they have to work completely differently. The Millennium Dome at Greenwich in London is the largest dome in the world, but it's quite unlike the more conventional dome structures we've seen. It's very thin and it seems to hang in space, held in a cat's cradle of steel wires. But is it really a dome? Well, it's clearly dome-shaped, but the forces at work in this structure are the opposite to the domes in Paris and Florence. Instead of forces pushing from the top down, this dome is being pulled into shape from the base. The shell of this dome is in tension. Unlike our previous domes, whose shells were self-supporting, the Millennium Dome is held in shape by its masts and cables. Basically, it's like a tent. Construction began on the 23rd of June, 1997. It was a mammoth job to organize the people and equipment required to build the dome on schedule. The concept of the dome came about only recently. In 1996, a series of exhibition structures were being developed to celebrate the millennium, but it seemed inefficient to make each of them weatherproof, particularly if they were only going to be temporary. Covering the whole show under a single umbrella would create a focus and simplify the design of the individual exhibition stands inside. So the idea for the Millennium Dome was born. A year on, and construction of the main structure is nearly complete. It's an incredible achievement to have got this far, this fast. It's a huge building site at the moment, and it's a fantastic time to see it, because when the exhibition is in place, it'll be very hard to see the structure. The dome will be twice as big as the Georgia Dome in Atlanta, 320 meters in diameter, and the perimeter is 1 kilometer long. The most dramatic feature of the whole structure for me are the cables which form a giant net in the sky.
Around the opening at the top is a tension steel cable ring. All the cables pull outwards on this, and it's vital to the stability of the whole dome.
It was particularly important to make sure that any damage up there did not result in the whole tent unzipping. They managed this by using 12 intertwined cables so that even if one broke, the others would be able to share the load.
These are the stringers which radiate out from the center. Other cables hold them firmly in position at intervals of 25 or 30 meters.
To keep the stringers taut, they're stretched to 2/3 of their peak tension, a load of 40 tons in each cable. This means that they're virtually straight between their supports, which in turn makes it easier to hang the fabric panels.
When any material is stretched like this so tight, there is a risk that a panel rips and then it might overload the next panel and so on. So to protect against this and to stiffen the structure around the perimeter, these stringers are linked by cables which run right around the dome in a circle. But, and this is a neat trick, they couldn't lie in the fabric, so they are held up above the panels using these rigid wishbones and crisscross cables.
Each of the masts is 100 meters high, and they do all the work to hold the dome up. The weight of the dome isn't great, but the masts must collect and channel all the tension forces down to the ground. Each mast carries a compressive force of 1,000 tons, spread down through these 4 struts at the bottom and carried into the ground through the concrete foundations. These backstays hold the mast in position and tension it down to anchors under this concrete block, screwed into the ground like giant tent pegs. The mast is trying to pull up on the anchors back towards the dome, and this concrete slab helps to hold the anchor in position, pushing out from a giant concrete ring beam all around the perimeter.
The fabric which has been chosen for the dome had to be translucent, strong, and long-lasting. It's a glass fiber material, coated in Teflon and only 1 millimeter thick. Compare that to the 4-meter thick shell of the Duomo in Florence.
There were other cheaper choices, such as a PVC-coated polyester, but it wouldn't have been so long-lasting and it would have absorbed dirt. This should remain cleaner for longer.
The Millennium Dome is a landmark in the history of engineering achievement. It's a structure which could not have been built even 20 years ago. It reflects huge advances in computer techniques and material development, which are all part of the excitement of building. But in the end, this dome is all about celebration. For good or ill, it reflects our time in that it is adaptable, temporary, and built to mark a specific moment in history. So the Millennium Dome is very much of its time, both in its engineering and in its function.
As we've seen, domes are all about communal space, bringing people together. Their very shape inspires a sense of wonder, grandeur, and security. And that's why, for thousands of years, we've continued to build them, ever bigger.
In the next program, it's off to Italy for a rare trip up the world-famous Leaning Tower of Pisa, then across the Mediterranean to Spain to marvel at the twin wonders of the Torres Puerta de Europa in Madrid, and ask what keeps the Torre de Collserola in Barcelona still standing.
Sometimes buildings seem to defy gravity.
In this program, we're going to look at the ancient Leaning Tower of Pisa, the incredible Puerta de Europa towers in Madrid, and a modern classic, the Torre de Collserola in Barcelona.
Buildings and structures rely on their foundations to keep them upright, and their foundations rely on the ground beneath. The challenge is to find a solution which uses the ground effectively and doesn't overload it.
To explore this subject, we're at the site of one of the most famous structures in the world, in the beautiful Italian city of Pisa. The Leaning Tower is the campanile or belfry of a large complex of religious buildings, including the great cathedral, the baptistry, and an ossuary dating from the medieval period when Pisa was at the height of its power. Built to a height of 179 feet, the tower is essentially a hollow cylinder containing a spiral staircase that ascends to the bell. Both the inner and outer surfaces are faced with white marble.
Construction on this remarkable building was begun in 1173 by Bonanno Pisano. At that time, the sea was a lot closer to the town than it is today, and Pisa was a rich and successful naval republic. The bell tower was to be one of the tallest campaniles in the land, to call the Pisans to worship.
Records suggest the building began to lean as soon as the first floor was completed. What is known for certain is that building work stopped in 1178 after reaching the fourth floor and was not started again for 100 years. The Pisans had to go to war with Genoa.
The reason for the tilt lies in the soil beneath the tower. The soil here is a soft clay, highly compressible and sensitive to changes in groundwater level. In this case, that means changes in the sea and the river, and crucially, from the effects of the construction of the then new cathedral just over there. It was a bit like trying to build a tower of bricks on a soft mattress.
By the time the construction had reached the fourth floor, its weight was 9,500 tons, and one side had gone down half a meter relative to the other.
It's such a strange feeling on the staircase, because here on the south side, it's as though the stair is leaning away from you, and suddenly you climb around the corner, and the stair is absolutely precipitous. It's nearly vertical. As the soil consolidated over time, more on one side than the other, it became stiffer, and the direction of lean changed from the north to the south. But nevertheless, they kept going. Construction was restarted in 1272 by Giovanni di Simone.
After 6 more years of building, the tower weighed 13,800 tons, and the settlement on the south side had reached nearly 1 meter. The bell chamber was finally built between 1360 and 1370, but to make the bells hang straight, the bell chamber obviously had to be vertical.
Here on the overhanging south side, there are 1, 2, 3, 4, 5, 6 steps up to the bell chamber. But here on the opposite side, there are just 1, 2, 3, 4 steps up to the same chamber. This is what gives the upper part of the tower its characteristic curved shape. It's an extraordinary structure, a real achievement for its day. Today we understand more about the properties of the soil below and the stability of the tower, but to the Pisans of the 13th and 14th centuries, their moving tower was nothing short of a miracle. It was a sign that God was on their side in the wars with Genoa, a sacred icon, a place of pilgrimage. As we come around the side of the tower here, we can see where the stone's been pulled apart by the tower leaning over. Masonry is an incredibly robust medium, and this is just a perfect demonstration of that. Here there are cracks opening up and then closing, and here the stone's been actually chipped off in the corner where it's been forced together. Lovely. Over the centuries, as the tower continued to lean and sink, it pushed up a mound of earth on this side, which helped to slow up the movement. Amazingly, to reveal the stonework, this was excavated in the 1830s, after which the rate of lean increased dramatically.
In 1990, it was recognized as a danger and was closed to the public. At present, the tower leans some 15 feet from the perpendicular, putting huge stresses on the south side. The tilt is increasing all the time, and in the early 1990s, the tower was also found to be rotating.
Works are now in progress to stabilize the tower for good. The Italian government was finally spurred into action following the collapse of a civic tower in Pavia. The first step was to secure the tower temporarily.
Tons of lead weights were attached to the north side in an attempt to stop the tower from leaning further. But a more permanent solution was required.
The only sensible solution to stop it falling over is to change the angle of the tower. Early schemes proposed props, but it would be very risky to work under the leaning side. The solution that's been adopted is neat and simple and doesn't even involve touching the tower. Small volumes of soil are extracted by drilling down under the tower from various points around the north side, leaving tiny cylindrical cavities. These then squeeze shut due to the pressure under the tower. By choosing in which areas to excavate, the tower can be steered back from the brink.
If successful, and trial results are so far looking positive, the repairs will extend the life of the tower by 200 or 300 years and should stop the rotation completely.
The aim is to reduce the angle of tilt by ½ degree. That's just about ½ meter at the top. Of course, they don't want to straighten the tower completely, because at the end of the day, it's the lean that brings the visitors.
The medieval masons must have been in awe of their moving tower, not understanding the subtle movements in the soil beneath. Pisa lost the war with Genoa, but its tower has assured its place in the world.
But what if you really wanted to design a leaning building? Well, that's exactly what's just been done recently in Madrid.
The incredible twin towers of the Torres Puerta de Europa straddle the main road north out of the city. Translating as Gateway to Europe, the towers are both office blocks, one occupied by one of Spain's major banks. For me as an engineer, these structures are simply unique.
Wow. They're absolutely fantastic. Look at these huge, great black towers leaning right over the road to Madrid. Each one leans 3 times as much as Pisa, and they're twice the height. Not a lightweight piece of architecture, this. It's a really powerful statement.
But these buildings aren't just Latin exuberance. There's a good reason for their extraordinary design.
At the planning stage, restrictions on the site meant that the towers had to be 140 meters apart at the base, potentially diluting their impact if they'd been ordinary vertical buildings. The architect decided to link them visually by leaning them together. It's a bit of a stunt, but it works. They really dominate the whole space. Inclined buildings are very unusual and they require special engineering design. But the principles are simple. The most critical question is the most obvious. How do you stop them toppling over?
The overhanging upper stories want to tip the building forward, so the simplest solution is to weigh it down at the back in the foundations.
Down below me, under each basement, is 14,000 tons of concrete, acting exactly like the lead weights in Pisa to counterbalance the lean of the building. That's enough concrete to cover this entire area 10 meters deep. So the counterweight stops it toppling, but what stops it bending and sagging? Every building has to be stiff enough to hold its own shape, but in these inclined towers, the problem becomes even more acute. The steel and concrete frame of the building has to form a rigid skeleton holding it upright. So the shape of the frame is very important.
The great silver triangular shapes that you can see so clearly on the side of the building give it a lot of stiffness. Triangle shapes are useful in building frames.
And I can easily show you why by sketching it. Use a napkin. Imagine a three-sided shape and a four-sided shape, and we try to squash them by applying forces at the corners. The three-sided shape stays rigid because none of the bars can move anywhere. But the four-sided shape is easily flattened. So the triangle is a much stronger shape in structural terms.
The problem of the building sagging is most serious during the construction of the frame, before the building has its full stiffness. So to correct this, there's another system to keep it stiff.
Imagine my arm was the building. If I stretch this rubber band, it pulls my fingers back and straightens and stiffens my arm. Down the back of the building here, there's a system of steel cables running from the top to the bottom, anchored to the foundation, which does exactly the same job.
During construction, by tightening up the cables, they use them to straighten the top of the building by 150 millimeters. And if they need to, they could still tweak it further today. It's called post-tensioning. If you look at the space between the top and the bottom of the building, there's only a few meters in which they overlap. It's in this space, between the top and the bottom, that a huge concrete backbone supports the construction.
Wow, and here it is. The concrete core is huge at the bottom of the building, and it also houses the lifts. Let's take a trip up. Here at ground level, you can see the street outside. The lifts are at the front of the building. We'll see what happens when we get to the top. Right, here we are. At the back of the building. There. Well, this is the top of the highest building in Madrid, and there's a heliport here. Isn't it fantastic? What a view!
When they were completed in 1990, the Torres Puerta de Europa instantly became a landmark in Madrid. It's a distinctive gateway which dominates the local skyline.
Office buildings so often put costs before creativity. Most are very bland and boring, but it's really refreshing to see something so original. For the engineers, this must have been a very exciting project.
As we've seen, keeping a tower standing upright is all about controlling the forces going down. But across Spain, in Barcelona, we're off to find a fantastic expression of this. Barcelona has an impressive array of wonderful architecture, combining traditional Catalan buildings with flamboyant new design. Commissioned in the run-up to the Olympics in 1992, the Torre de Collserola is a state-of-the-art telecommunications tower.
Wow, fantastic. Coming up out of the city into the Collserola Park, green trees and a blue sky, you can really appreciate the stunning beauty of that white tower. 288 meters tall, it's almost as high as the Eiffel Tower, on top of a mountain.
There are 13 floors, all but one designed for satellite dishes and transmission equipment. In fact, the tower is big enough to house 700 people and relies heavily on brilliant engineering to keep it upright.
Traditionally, communication towers have mostly used open steel lattice structures, like the grey electricity pylon behind me. But if the new tower had been built in this style, it would have required an enormous base, and it would have looked like a giant industrial pylon, totally incompatible with Barcelona's stylish image. The city saw the new tower as a chance for something much more unusual.
A British architect, Norman Foster, won the commission. His design reduced the structure to its bare elements. The tower is a simple, hollow, circular concrete shaft. 13 floors are wrapped around it and held in place by a system of steel trusses and cable stays. Above the concrete shaft, an 80-metre telescopic steel tower, like a car aerial, reaches skywards. Right at the top sits a small crane for lifting equipment up and down.
Under the bottom of the tower, down there, the main foundation is a simple concrete disc, 20 meters in diameter and just 5 meters thick. It didn't need to be thicker because the tower is founded on rock, not soil. But such a tall, thin shaft would be much too flexible without another system to stiffen it. So the tower uses steel cables, like guy ropes, to hold it down, counteracting the effects of one of the major threats to towers, the wind. Up here, wind gusts can reach very high levels. The wind is known as the tramontana, and it blows from the northwest, rushing over the hills. Gusts can reach well in excess of 100 miles an hour. That's pretty serious. 3 sets of high-strength steel cables anchor the tower down to huge concrete blocks like this, each one 800 cubic meters, 2,000 tons of concrete.
The cables are tensioned so that even in a high wind they will never go slack, and that ensures the tower remains stiff.
In a 60-mile-an-hour wind, the top floor will move only 85 millimeters. That's just this much.
The huge forces in the steel cables pull down on the tower and up on the concrete foundations simultaneously. But any long tube under compression bends easily, so it needs to be braced.
The tower is a hollow shaft like this piece of tubing, but if I compress this between my hands, it bends and collapses easily. So how did the designers get around this when it came to the tower? Here we are on one of the floors of the tower that's still being fitted out. It's a curved triangle in shape, held up at each of the corners by a giant steel frame. The frame's pressed onto the tower by the cables which run down below and up to the top. Remember the tube? The frame acts like a brace around the tower, just like this, making it much stiffer.
Notice how lots of shapes in the structure are triangular. As in the towers of Madrid, this is where the tower gets much of its strength and stiffness.
There's a lot of equipment on the tower. This floor is for television. Each of these is a different local station. This one's for picking up outside broadcast units. Hope we don't get in the way.
You may be wondering how they built a 13-story block way up here. Well, the answer is they didn't. The floors were actually built on the ground and lifted up here by jacks. It took 4 days to lift the structure into place.
Finally reaching the top floor, inside the concrete shaft, stretches way above us. But we can't get out that way.
These cables from the top of the frame to the top of the tower cross in front of the microwave dishes. They're made of Kevlar, an immensely strong man-made fiber, as strong as steel. But unlike steel, Kevlar cables are invisible to radio waves. We're 155 meters above the bottom. This great tower is quietly buzzing away. But all around us, these cables, the steel frame, and the concrete shaft are all carrying huge forces, locking this extraordinary structure into its exact position. It's a masterpiece of engineering. There's no doubt that the tower met with the city's brief to construct a monumental technological element. The tower is unquestionably a dramatic symbol of Barcelona's commitment to innovation.
Engineering is the art of the possible. To make the Leaning Tower safe for the future, to break with convention in Madrid, or to combine beauty with function here in Barcelona, all have taken extraordinary ingenuity. And that's what it's all about.
In our next program, we sail to the Eddystone Lighthouse in Plymouth, investigate the gigantic floodgates protecting Rotterdam from the sea, and fly out to the largest structure ever moved on Earth, the Troll gas platform. The sea can be one of the most hostile environments known to man. Storm winds, huge waves, and salt water all take their toll on any structure, either here on the coast or out there. To cope with these threats, we've had to find solutions.
In this program, we investigate the gigantic floodgates protecting Rotterdam in the Netherlands. Visit the Troll offshore platform, the largest structure ever to be moved across the face of the Earth. But we begin in Devon, southwest England. Plymouth is an historic naval city and fishing harbour in the southwest of England. It stands at the entrance to the English Channel in one of the most exposed corners in Britain, and therefore it's no surprise that for centuries its treacherous approaches have been protected by a number of lighthouses. we're off to the site of the famous Eddystone Lighthouse, which lies 14 miles out on the Eddystone Reef. The Eddystone Reef is the site of several historic lighthouses, and it's their changing designs that reflect our increasing ability to withstand the elements. There has been a lighthouse at Eddystone since 1699, but the ferocity of the weather in the Channel has claimed 3 of them. Indeed, one was completely swallowed by the sea in Britain's worst ever storm in 1703. The present tower was built by James Douglas in 1882, but it's one of its predecessors, that of John Smeaton, that we're interested in.
The first lighthouses on this site were built of wood. The men who built them advocated wood because of its flexible qualities, but they were either lost to sea or burnt down. John Smeaton's tower, built in the 1750s, was a much greater success. You can see the remains of Smeaton's tower here, near the base of the new tower. The rest of it was taken back to the mainland, stone by stone, to be preserved.
The current tower, now over 100 years old, remains unscathed by the elements, but the reason for its survival can be attributed in part to the pioneering work of John Smeaton. This is the Smeaton Lighthouse, which was brought back from Eddystone Reef and rebuilt after it was decided that it be replaced by a taller tower. Smeaton proposed a building which was said to be based on the shape of an oak tree. He said, "My main aim is to construct a tower whose every part should be strong in direct proportion to the stress it's likely to bear." Smeaton also pioneered new materials and construction techniques, inventing a large crane for lifting the large stones from a boat moored next to the site.
However, his major contribution was to recognize the importance of interlocking the stones to give the tower additional strength. The intricate shapes fitted together a bit like a jigsaw puzzle, using dovetail joints and iron and marble dowels to lock the whole structure together.
The higher up the lighthouse you go, the thinner the walls become. They are made from a granite called moorstone, which is very dense and resistant to weathering. Here at the top of the lighthouse, the keepers would ensure the flame burned constantly throughout their long stays. This frame held the candles, one in each of the holes.
Smeaton's tower on the Eddystone Reef was finished in 1759, 3 years after starting work, and its 24 candles burned in this lantern for over 100 years. In its day, it had to endure force 12 storms, and at one time, according to the keeper in 1824, the water came from the top of the building in such quantities that we were overwhelmed.
What finally overcame his structure was the rock it stood on. Storms undermined the rock foundations, and by 1877, Smeaton's tower was finally retired. As an acknowledgement of his great achievement, the tower was rebuilt here on Plymouth Hoe. Lighthouses need to withstand the sea, but they could never claim to hold it back. For that, something truly amazing is required. To the east of the English Channel lies the North Sea coast of Holland. With much of the country below sea level, the Dutch live under the very real threat of disastrous flooding, and much of the coastline is protected by a series of fixed barriers and dikes. Rotterdam is the biggest port in Europe, and the problem for the government was how to protect the city from the might of the sea, while keeping its main waterway open for the hundreds of ships that passed down it every day. The solution was a pair of huge floodgates that, in the event of an emergency, will swing out into the waterway and meet in the middle, stopping the sea in its tracks.
The barrier was opened in May 1997 at a cost of £400 million, and it's beautifully simple in its operation. It comprises two enormous, identical gates which are floated out from dry docks into the river and sunk onto the river bed. This is the gate on the north side, and I'm walking along the sea wall. On my left is the giant truss that holds the wall in position, and the joint that holds the whole gate to the shore. The sea walls are 210 meters long and 22 meters high. You can see about half of them here. The other half is down in the dry dock. They're hollow, so they can be floated out into the river like a ship, where the two halves meet. Then they're ballasted with water and they sink to the riverbed. We're lucky today that the dry dock's empty, so we can get right down into the bottom and have a look at the shape of the seawall and how it's floated out. But it's pretty muddy down there, so I need some boots. One of the great advantages of the dry dock for this design is it means that the maintenance is much easier. Right, let's go. Fantastic. You can see right underneath it. Here we go. Ah! If a storm surge arrives, then the whole dry dock is flooded, the wall floats up and is pushed out into the river. After the storm has passed, they float the wall back into the dock, sink it back onto its supports, pump the water out. The mud comes in when they open the gates as well. Let's try and see the shape of it a bit better. When it's out in the river, it sinks like this onto the seabed because, of course, it's held right back on the shore. So it's floated out, and then it sinks onto the seabed. And the great wall here provides the main barrier to the storm wave coming up the river. But when we get right underneath the wall, we can see the ceiling edge where it sits on the bottom of the river. And this is it. This rubber piece here, which runs right along the bottom of the wall, is what sits onto the concrete sill at the bottom of the river. It gets squashed under the weight of the wall above, and it's sitting on pistons, so it can just squidge up a little bit and provide a really good seal underneath the whole wall. Behind the gate there is the river, way up there. And these great ports are where they let the water in to fill the dock. Perhaps we better go. Let's go up onto the back of the wall and we can see how the force is taken out to the shore.
Supporting the Great Sea Wall is a huge truss. There are 8 main struts which take most of the force from the sea and carry it directly along the arms into the foundation. Other smaller struts above provide bracing against the whole gate twisting.
Each of the gates is the size of the Eiffel Tower lying down, but they weigh twice as much. The arms are made up of giant trusses, here made with cylindrical steel tube, all welded together.
The two great arms that hold the seawall meet here. Their great length and the huge forces in the members mean that they're susceptible to buckling, so the trusses are very deep and heavily braced.
At the end of the gate, where the arms come together, is the pivot mechanism around which the whole gate moves.
Wow, absolutely gigantic. The huge force from the seawall is carried down through that giant truss and ends up here on this knuckle, this enormous ball joint. It's 10 meters in diameter, the biggest ball joint in the world. Under a storm load, 35,000 tons of force arrive right here. Climbing down inside the ball here. There we are. This is right inside the ball itself. It weighs 680 tons, and of course it can't be left just to sit on its socket when it's not being used. So these great pistons, 6 of them, can lift the whole ball up when it needs to be painted. Keep your fingers out of there. The whole ball turns on these bearings here when the gate is closed, bringing the face of the ball into the great grey socket that you can see behind me. Under the storm force, there's a huge pressure on this face. The pressure on the face is the same as a submarine would feel 1,800 meters underwater, 6,000 feet down. That huge pressure is passed through the steel shoe and into the concrete foundation here. And the whole foundation would give about 200 millimeters when the gate is closed. It's absolutely amazing. Rotterdam's storm surge barrier is engineering on a grand scale, ingenious in concept, beautifully executed and immaculately maintained. But both our structures so far have been land-based. If we're talking about the sea, we'd better get out there.
Off the coast of Norway, beneath the North Sea, lies the Troll Field, one of the richest areas for oil and gas deposits in the world. The challenge is to build a structure that can stand firm in the deep sea and against ferocious storms while providing a platform from which to tap the vast resources below the seabed. We've come to Bergen in Norway to go out to Troll A, a gas platform and the tallest concrete offshore platform in the world. The potentially dangerous journey out into the North Sea is only possible by helicopter, and so it's necessary to don a survival suit for the flight. The Troll Field lies 60 kilometers from the Norwegian coast, and the natural gas beneath it was created more than 130 million years ago. The immense amount of gas in the field meant that a permanent structure was needed, one that would stand in place and extract gas for over 50 years.
And there it is. Isn't that fantastic? 4 great concrete legs coming out of the sea. What a sight.
The drilling deck and superstructure of Troll A sit on 4 massive concrete legs that reach down over 300 meters to the seabed. The base of the platform is made up of 19 concrete cells that were built on land. The base was towed out by tugs and sunk into a deep fjord where the 4 towering legs were added. At 369 meters, each completed leg of Troll A is taller than the Eiffel Tower. The whole structure was then sunk further down into the deep fjord, and the platform was aligned over the top using barges. Water was then pumped out of the structure, allowing it to float up a matter of centimeters to meet the platform. The completed structure was then refloated in preparation for the journey out to the Troll Field. The platform was towed out to sea, making it the largest structure ever to have been moved across the surface of the Earth.
Up here on the helipad, I'm 76 meters above the sea. It's easy to forget that most of the structure is underwater. It's a bit like an iceberg. So right up at this height, I'm actually exactly the same height as the top of the Empire State Building. An offshore platform like this is really a chemical plant at sea. And because it's an industrial plant, that's why I'm wearing yet another set of protective clothing. Down there is the gas plant, and in the distance, the grey section is for processing the gas, and here in the middle is the drill rig. This new platform hasn't finished drilling all its production wells yet. There are going to be 39 in the end, down into the seabed, and then fanning out to a depth of about 1.5 kilometers. They reach out for half a kilometer all round the platform. Above us are the drill stems, hanging like in a wardrobe, ready to be used. On average, it takes a month to drill each of the wells to extract gas. But what we're really interested in is what makes this structure stand up. And to do that, we need to go down to the seabed itself.
The journey down to the bottom of the sea is by a lift inside one of the great legs.
It's so quiet, it's really eerie. You have the feeling that with the sea outside, you're just on another planet. On land, you see tall buildings, you see tunnels, you see other gigantic structures. But here, in this environment, the scale of this engineering and its achievements are really extraordinary. You really feel there isn't anywhere on this planet or any other planet we couldn't go. The pressure of the sea outside, just outside the wall, is 30 times the pressure inside here at the bottom where I'm standing, trying to squash the leg like this. The reason it can't is a combination of the strength of the heavily reinforced concrete and the cylindrical shape, which is the most efficient shape to resist that sort of external pressure. Just the same principle as a submarine hull or an aircraft fuselage. Down here, right at the very, very bottom of the platform, is where the pipelines turn the corner and head out over the seabed, taking the gas to Norway, 60 kilometers away, down there. And under my feet, there's a concrete floor, and under that is the mud. And the whole platform is embedded deep into the seabed. It's like a bunch of upturned coffee cups, 19 of them, and we're just in one of them. And they've been pressed into the seabed with the wall of the coffee cup pushed deep into the mud. And if you can imagine pushing a mug into mud, trying to pull it out, the suction inside holds it firmly in place. And that's exactly how this base works. Bit of a leak over there. Hope it's not too serious. No, it's just a leaky valve, really. Just collecting up some water. This might look like graffiti, but actually it's the visitor's book. And I've been invited to sign my name.
I'm back on the main deck level, at the top of the concrete legs. Down on the sea bed, the problem was to withstand the huge pressure of water. But up here, near the top, it's the forces from the wind and the waves pushing on the platform. It's a quiet day today, but in a storm, waves can reach the deck right up here, 30 meters above sea level. That must be pretty frightening.
But the deck is high enough to avoid being swamped by the waves and is securely attached to the 4 great concrete legs, which are strong and stiff enough in bending to withstand the estimated 5 million waves that crash onto them every year. It's structures like the Great Troll platform and the engineering advances behind them that give us the confidence to know that we can live and work alongside the sea, whatever the conditions. It's no longer a question of seeking refuge from it, but of knowing we can coexist on shore and in the deep oceans. In our next program, we look at arches. We start our story at a towering Roman aqueduct, the Pont du Gard in Nîmes, France. Then witness the Gothic splendor of Cologne Cathedral in Germany, and we travel across the country to explore the cavernous Lufthansa aircraft hangar in Hamburg, big enough to house 3 jumbo jets.